Hello everyone, my name is Wilfred Abija. I am a plant breeder. Today I'm excited to share with you some information. Keep tuned, subscribe. I'm going to talk about Bayes' theorem. And Bayes' theorem is nothing but application of conditional probability. Therefore, for you to apply Bayes' theorem, you need to know how to use conditional probability. Bayes' theorem helps us to solve difficult probability issues, and it's one of powerful theorems that we have in probability. Now, let's to start to talk about conditional probability, let's consider two events occurring, event B and event A. Now, in conditional probability, you can be asked, what is probability of event B occurring given event A has occurred? This sign here means given. Therefore, it's read, what's probability of event B given event A has occurred? Now, let's look closely at this. This event B and this event A. This their point of intersection called point B intersection A. Therefore, getting the probability of event B given A has occurred, we assume that the whole sample space shrinks to A. And if all the sample space becomes event A, we'll have this intersection remaining here. So event A and this intersection here. Therefore, probability of event P given A has occurred is the probability of intersection B and A. This intersection here is this one. Is the probability of B intersection A divided by the probability of A. Is this intersection divided by this whole probability of A. That's probability of event B given A has occurred. Conversely, if you are asked what's the probability of event A given B has occurred, you assume that this sample space has shrunk to probability of event B. So it has come here, but the intersection remains here. Therefore, the probability of A given B has occurred is the probability of intersection A and B divided by B. Let's continue. Let's summarize this. If you look at these two events, B and A, probability of event A given B has occurred, you'll consider this sample space B with intersection A and B. And if you are asked probability of event B given A has occurred, you consider this one A with intersection A and B. Therefore, if you look closely, intersection A and B is this one here. Intersection B and A is this one here. Therefore, this intersection A and B is equals to intersection B and A. So, to compute this getting intersection A and B, probability of intersection A and B is equals to probability of this times this. This is what's written here, which is equals to probability of this times this, which is this one. This is our equation 1. You have to know that probability of intersection A and B is equals to probability of A given B has occurred times probability of B. Is also equal to probability of B given A has occurred times probability of A. If we move this one, this point green equation here, down here, it will appear like this. And if we are interested with probability of A given B has occurred, we divide by probability of B on both sides. And if we do that, probability of event A given B has occurred will be probability of event B given A has occurred times probability of event A, which is this one, divided by this one, probability of B. And this is the Bayes' theorem. We can expand this theorem a bit. Consider these events here where event A1, A2 and A3 has occurred, and they are mutually exclusive and they add to 1. A1 plus A2 plus A3, they add to 1. What if another event occurs occurs that overlaps on these three events. Let's look at that. Event B has occurred and has overlapped A1, A2, and A3. Event B has this intersection A1 and P, intersection A2 and P, intersection A3 and P. If we add intersection A1 and P plus intersection A2 and B plus intersection A3 and P, it will give you to P. Therefore, probability of having P is A1 intersection B plus A2 intersection B plus A3 intersection B. But from our question 1, you remember, probability of A intersection B is equals to this from the first equation. To get probability P, we can substitute this with this or this one with this. I prefer substituting this with this because we are looking at probability of P, and this one starts with probability of P given event A has occurred. Therefore, probability of P is equals to A1 intersection B, which can be probability of P is equals to probability of P given A has occurred, A1 has occurred, times probability A1 plus probability A2 intersection P, which is equals to probability P given A2 has occurred, plus probability A3 intersection B, which is equals to probability of P intersection A times probability of A3. Therefore, we can rewrite this equation here by substituting this with this one. Therefore, probability of B is equals to probability of event P given A1 has occurred times probability of A1, which is this one, plus probability of event P given A2 has occurred times probability event A2, which is this one, plus probability of P given A3 has occurred times probability of A3, which is this one. If we sum up this one, we'll get probability of P is equals to probability of P given AI has occurred times probability of event A sub I. Summation, because we are adding this and this and this 1, 2, 3 and blah blah. So if you have understood this, equation 3, which is a short form of this is our equation 3. If we look at our equation 3 and bring our Bayes theorem equation 2 here, we can substitute probability P with probability P here. If we do that, we get this one here. Now this is the extended Bayes theorem. This one we have replaced. Now let's have an example. Consider the mating of two heterozygotes, A1, A2 and A1, A2, and their progeny Y, which have appearance of dominant phenotype A1, A1 that has a probability of a third, or A1, A2 with 2/3 probability. Let me explain this. Here we have this cross, and this cross has an offspring which is called Y. This offspring we have considered only dominant phenotypes. That means a recessive has been removed from the consideration. Therefore, we remains with the 3 dominant phenotypes with A1, A1, which is a third, or A1, A2, which is 2/3. Suppose Y, this A1, A1 and A1, A2 is test crossed with recessive, and the resulting end offsprings are dominant A1, A2. What's the probability that Y is homozygote? In other words, what's the probability that the test cross was A1, A1 times A2, A2, given that it produced dominant offspring? To make this simpler, let me put it in a diagram. This question means that we have these two parents, A1, A2 and A1, A2, and they have given to these 4 progeny. Out of these 4 progeny, only 3 progeny were considered. This recessive was not considered. So 3 progenies were considered. And of the three progeny, A1 is a third, and A2 is 2/3. And this Y progeny here was test crossed by A2. And all offsprings were N dominant A1. Now, what's the probability that this cross which produced this was between A2 and A2 times A1? Now the question is, can be put in a conditional probability format using Bayes' theorem. Probability of having this cross A1 and A2 given any dominant offsprings. To compute this, the probability given n dominant offspring has occurred is probability n dominant offspring given A1 and A2 cross has happened times probability of A1 times A and A2 divided by probability of dominant offspring. This comes from the Bayesian theorem. Now, from genetics, we know that to get a probability of an offspring, maybe this recessive here, is probability of parent 1 and probability of parent 2 and the probability of offspring. So probability of this red offspring is equals to probability parent 1 and probability parent 2 and probability of offspring. So to get a probability of n dominant offspring, we have two ways you can get dominant offspring. Either crossing A1, A2 with A1, or crossing A1, A2 with A2. So we have two ways of getting dominant offspring. It's either by crossing A1 by this recessive or crossing A1, A2 by this recessive. So a probability of getting a dominant offspring, any dominant offspring, is the probability of offsprings times probability of parents. And parents can be A1 of a cross between A1 and A2, or it can be A1, A2 and A2. But if this A1 and A2, the probability of these parents is a third. Why? We are certain that A2 is going to be there. Therefore, since we are certain, the probability of A2 is 1. But the other parent we are not certain. However, A1, the probability of A1 is a third. Therefore, a third times 1 is equals to a third. And if this cross occurs, we are certain that A2 is going to be there. Therefore, probability of A2 is 1. But we are not sure that A1 is going to be there. The probability of this is 2/3, which we are given, making these parents have 2/3 probability. So therefore, these are parents. The parents here is a third, and here is 2/3. Now let's look at the probability of offsprings, which we can get either in this cross or this cross. If this cross happens, then the probability of dominant offspring is 1. Why? We are certain that this one parent is going to be there. Therefore, the probability of this parent is 1 times, we are not certain that this one is going to be there. But if it comes, then the cross of this and this will give A1, A2. All offsprings will be dominant. So if we get this and this, we are sure that all offsprings are going to be A1, A2, which is dominant. Therefore, probability of getting dominant offspring given this cross is 1. Therefore, probability of dominant offspring and this one is 1 times a third. The same applies to here. Probability of getting a dominant offspring given A1, A2 times recessive. If this occurs, because we are certain that this parent A2 is going to be there, all the offspring will be a half A1, A2, and a half A2, A2. Therefore, n dominant will be a half n offsprings. This is what's here. Probability of dominant offspring given this is here, because we are sure that this one is going to give all of them A1, A2. Therefore, the probability of having this offspring is 1 raised to the number of springs, which is in n. If there are 4, is 1 times 1 times 1 times 1, 4 times. But if there are n, is 1 raised to n, which is 1. N number raised to n is 1. 1 raised to 1000 is 1. 1 raised to 0 is 1. Probability of dominant offspring given A1, A2 and A2, A2 cross has occurred is a half n offspring, because we are certain that this parent is going to be there. If the other parent is this, then a half offspring are going to be dominant and half recessive. Probability of n dominant offspring is a half raised to n. If we combine this, probability of dominant offspring is this times a third. This is 1 times a third. It's 1 times a third plus this times this. This is a half n times 2/3 is this one. So using this formula here, we can substitute probability of n dominant offspring given A1, A1 and A2, A2 cross has occurred is this one, 1 times this probability A1, A1 and A2, A2 cross has occurred. This cross is here at that, is 1 times a third, divided by probability of n dominant offspring, this one here. If you solve this, then you have the answer of probability of cross A1, A1 and A2, A2 occurring given n dominant offspring has occurred.